Hello everybody, and welcome to our video on indeterminate forms and L'Hopital's rule. So what we're going to be looking at here is L'Hopital's rule. This is a pretty powerful but also finicky rule that can help us deal with certain limits which we didn't have the tools for before. So I always like to warn students that L'Hopital's rule is like a sledgehammer. And if you're trying to hang up a picture on the wall, you don't get out the sledgehammer to put the nail in. So you only got to use this when you got to knock down a wall. Now that is going to happen, and we're going to see some examples of problems where it's appropriate to use L'Hopital's rule. But typically, it's best to go back to your standard approaches that we learned at the beginning of this course whenever possible. So with that being said, let's go ahead and recall a definition. If the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals 0, then the limit as x approaches a of f of x divided by g of x is said to be of 0 over 0 indeterminate form. Okay, and now we're going to introduce another form of indeterminate form. If the limit as x approaches a of f of x is plus or minus infinity, and the limit as x approaches a of g of x is plus or minus infinity, then the limit as x approaches a of the quotient f of x divided by g of x is said to be of infinity divided by infinity indeterminate form. Okay, so both of these things are our standard basic indeterminate forms for these quotient expressions. Now, as we've seen, oftentimes with these 0 over 0 or infinity over infinity indeterminate forms, we have approaches to deal with those, as we did earlier in the class, but not always. And one little thing I want to add, this a could also be infinity. These definitions still apply if x is approaching infinity or negative infinity. Okay, so theorem. L'Hopital's rule. So I will point out one silly little thing. L'Hopital's rule, the proper spelling of his name is El Hospital, though that is not his name. It's L'Hopital. Many times you will see this misspelled with just an O and no S. They do that to get people to hopefully pronounce it more correctly, but actually the spelling does look like hospital, but it is L'Hopital. All right, so suppose that f and g are differentiable with g prime of x not being equal to 0 near a, except possibly at a, and that the limit as x approaches c of f of x divided by g of x has 0 over 0 or infinity over infinity indeterminate form. Then, the limit as x approaches a of f of x divided by g of x will be equal to the limit as x approaches a of f prime of x divided by g prime of x. Okay, so you really have to make sure that you check indeterminate form, or L'Hopital's rule does not apply. We'll see an example later where if you try to apply L'Hopital's rule to something that is indeterminate, you will often get the wrong answer. So you have to check this every single time. All right, but we're going to just take a look at a little visual justification here. So we've got two curves here, call them f and g. So we'll say this one is f. And this one is g. Doesn't matter which we call which. So if you think of zooming in at the point where these two curves are passing, we see that the curves will look very similar to the tangent lines at this point. But the ratio of the tangent lines is given by the slope of f, the tangent line of f, times x minus a, divided by the slope of g times x minus a, which is just the slope of f divided by the slope of g. And when I say the slope of those functions, I mean the slope of their tangent lines, these here. So in other words, if those slopes are the same, if that ratio is the same, then taking the limit as x approaches a of f of x divided by g of x, it should act the same as taking the limit on these curves close to the point, on these straight lines. But the limit of those straight lines is just the slope of f over the slope of g, the tangent lines again. So in other words, we can say that, hey, taking the limit of this quotient f over g is equivalent to taking the limit of f prime over g prime, because we should expect to get that same ratio between the tangent lines as we got for the original functions. Okay, so we're not going to prove this one rigorously. We'll just go with that visual justification and jump into some problems. So, as I said before, we always want to check that these are indeterminate form so that we don't evaluate this incorrectly. So here I see the limit as x approaches 0 of x squared over 1 minus cosine of x. Okay, when I plug in 0, I get 0 over 1 minus 1, which is 0. So this is 0 over 0 indeterminate form. We'll just put a little note acknowledging that. And so when I apply L'Hopital's rule, this just says take the derivative of the top and take the derivative of the bottom. So I get 2x over, derivative of 1 is 0, derivative cosine is negative sine times a negative 1, that's a positive sign. Now when I look at this, I go, oh, this is still 0 over 0 indeterminate form. So we apply L'Hopital's rule again. And yes, you can apply L'Hopital's rule repeatedly as long as it's still an indeterminate form each time. You'll notice here we're no longer an indeterminate form. We have 2 over cosine of x. That's not an indeterminate form. Plug in 0, what do we get? We get 2 over cosine of 0, which is 1. And 2 divided by 1 is 2. All right, that's it for this example. So now we've got another limit here, the natural log of the square root of x over x squared. One thing I'm going to point out real quick to make our lives a little bit easier. Whenever possible, if you can use logarithmic rules to simplify the expression of a function, it's probably going to make your life a lot easier when you go to compute these limits. So I move this 1/2 in front. I get 1/2 times ln of x. So why is this such a big benefit? Well, if I had the square root inside, I'd have to apply the chain rule, and then I'd have a more complex function with that outer derivative here. So now I'm not going to have any chain rule to worry about, so it makes things a lot easier. So now I check this. When x approaches infinity, the natural log of x approaches infinity. And when x approaches infinity, squaring it certainly approaches infinity. So this is infinity over infinity indeterminate form. And that means we can apply L'Hopital's rule. And I always want my students to mark LH over their equality to let me know when they're applying L'Hopital's rule. That way it's easier to follow their work and understand their justifications. So this gives us the limit as x goes to infinity of 1/2 times 1 over x divided by 2x. Now you might be tempted to think this is in indeterminate form, but our numerator here is approaching 0 and the denominator is approaching infinity, and 0 over infinity is not an indeterminate form. But we can rewrite this a little bit to make it a little easier to evaluate. So 1/2 times 1 over x is 1 over 2x. And instead of dividing by 2x, I'll multiply by the reciprocal. And so this is the limit as x goes to infinity of 1 over 4x squared, which is 0. All right, that's it for that one. Let's go ahead and move on to another example. Okay, here we've got the limit as x goes to infinity of x squared over e to the x. So we check this, and x squared is approaching infinity. E to the x approaches infinity when x goes to infinity. So this is infinity over infinity indeterminate form. So when I apply L'Hopital's rule, I get the limit as x goes to infinity of 2x over e to the x. And when I check this, I see, hey, numerator still goes to infinity. Denominator still goes to infinity. This is infinity over infinity indeterminate form. So I can apply L'Hopital's rule again. And we get the limit as x goes to infinity of 2 over e to the x. Now my denominator is approaching infinity, but the numerator is just 2, so this whole thing is approaching 0. Okay, so let's take a look at an example. What if we don't check indeterminate form every time? So then what's going to happen? Well, let's start out by checking it, and then we'll do it the wrong way afterwards. So if I go to check this, I plug in pi. I see, well, sine of pi is 0. And this, so what do we get here? Sine of pi is 0. We get 1 minus cosine of pi, but cosine of pi is -1. So this is actually 0 over 1 minus -1, which is 0 over 2, which is 0. So this is not indeterminate form, and these are continuous functions at pi, so I can just plug right in and I'm done. But let's see what happens if we tried to apply L'Hopital's rule here. So again, this is not an indeterminate form. And I want to be clear that what I'm doing now is wrong. L'Hopital's rule does not work here. But let's just see it. Let's see if I try to apply L'Hopital's rule, what do we get? Well, the derivative sine of x is cosine. The derivative of 1 minus cosine is 0 minus negative sine. That's a positive sign. And so when I look here, cosine of x is approaching -1. Sine of x is approaching 0 from positive values. Right, we're in the second quadrant and sine is positive there. So that means this whole thing is approaching -infinity. Well, obviously that's not equal to this actual limit. So if you are not applying L'Hopital's rule, you are very likely to make mistakes like this that will lead you to get incorrect answers when evaluating your limits. So make sure you're checking that indeterminate form every time. Okay, let's go ahead and take a look at another example. Example 5 here. Evaluate the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. And I look at this and I go, hey, plug in 2 in the top and bottom, I get 0 divided by 0. That's indeterminate form. And you could use L'Hopital's rule here, but it's really silly to use L'Hopital's rule for a problem like this. This factors to x minus 2 times x plus 3. X minus 2 cancels. Now I can just plug in, that's 5. So using L'Hopital's rule on a problem where your basic algebra approaches works is really unnecessary and just adds extra work and extra room for error. So whenever you have these simple limits that we can use our previous tools for, just go back to using the previous tools. You don't have to use L'Hopital's rule on everything, and you shouldn't. It will often lead you to overcomplicate problems unnecessarily. Okay, well, done with that one. Let's move on to a new subtopic here. So now we're going to talk about indeterminate products. So here, if we have the limit as x approaches a of f of x equal to 0, and the limit as x approaches a of g of x equal to infinity, then the limit as x approaches a of f times g is said to have indeterminate form of type 0 times infinity. So we should be thinking of this like, hey, the numerator is pushing, or sorry, not the numerator, this factor is pushing the product to 0. The other factor is pushing the product to infinity. So it's like a tug of war. Which one is going to win? Is the function going to 0 going to win? Is g of x going to pushing to infinity going to win? Or are they going to find some compromise in between those values for the resulting product? So in order to do this, we have to apply L'Hopital's rule. However, L'Hopital's rule only applies to a quotient. So if we have f times g, we need to either rewrite this as f divided by 1 over g, or rewrite it as g divided by 1 over f. Those are the same things, right? Dividing by a reciprocal is the same as multiplication. So you can use either of these forms when dealing with an indeterminate product. So let's take a look here. When x goes to infinity, the square root of x is approaching infinity. Now for e to the negative x over 2, the numerator will be approaching negative infinity. That means the whole thing is approaching 0. When our numerator approaches negative infinity, e to that power approaches 0. So this is infinity times 0 indeterminate form. So now we have to rewrite this before we can apply L'Hopital's rule. And in this case, how to rewrite it is kind of obvious because I have this negative exponent for the exponential. So I'll just put the square root of x up top and rewrite it as a power with e to the x over 2 on the bottom. Now I've already checked indeterminate form. When I change this to a quotient, it's still going to be indeterminate form, but sometimes it's good to double check and go, oh, well, this is infinity. This is still going to infinity. This is infinity over infinity indeterminate form. Checking it again, once you've put it in quotient form, helps make sure that you haven't made a mistake in that process, right? If you started with an indeterminate form and you do the manipulation correctly, you should still have an indeterminate form. So it's a good way to make sure on more complicated problems that you haven't made any mistakes in between. Okay, so let's apply L'Hopital's rule. And we get the limit as x goes to infinity of 1/2 x to the negative 1/2 divided by, now here I got to apply the chain rule. So the derivative of my inner function is just 1/2 e to the x over 2. So that's nice, the 1/2s cancel. And since I have a negative exponent for that x now, I'm going to rewrite that in the denominator. And I get 1 over the square root of x times e to the x over 2. Now, both of these things are approaching infinity, so our whole fraction is just approaching 0. Okay, so let's go ahead and move on to indeterminate differences. So these ones are a little bit odd because every one of these problems, we don't have a nice general approach, right? The indeterminate products, you just know immediately you need to rewrite something as 1 over or the negative exponent of it, right? Just move it to the denominator. But when we have the indeterminate differences, that doesn't work. So each one of these problems is going to be pretty unique in terms of the manipulation you need to do. So we'll see an example of that. But you will usually have to think a little bit creatively to come up with this. So with this being said, we've got the limit as x goes to a of f of x is infinity. The limit as x goes to a of g of x is infinity. So then the difference, the limit as x goes to a of f of x minus g of x, is said to have a determinate form of type infinity minus infinity. It is very common for students to go, oh, well, infinity minus infinity, that's 0. Right? That is absolutely not correct, so definitely watch out for that mistake. And so I'll give you an example. So if I have the function f of x equals x squared minus x, you may be tempted to say that this is going to 0 when I take the limit, right? Limit as x goes to infinity of x squared minus x. You might be tempted to say that this is 0, but if we rewrite this in a slightly different form, it becomes clear when I factor out an x and I get x times x minus 1, that this is really a product of two things that are both approaching infinity. So the result is actually infinity. So the issue comes in here that although these are both approaching infinity, this x squared is growing much faster than the x to the first power. So because it's growing so much faster, it dominates the behavior of the function. And hence we just get infinity for our limit. Now for more complicated problems, we can't make this same sort of mental reasoning here. So let's take a look at an example where we kind of need this L'Hopital's rule here. So here we've got the limit as x goes to 0 of cosecant of x minus cotangent of x. So cosecant of x has a discontinuity at 0, and it's going to, well, depending on whether you're going from the left or right, it's going to plus or minus infinity. And the same thing is true for cotangent. It's going to plus or minus infinity. I suppose I should, let's go ahead and put this to 0 from the right, just to eliminate the odd other circumstances. So we'll just assume we're taking the limit from the right, meaning we're in the first quadrant for these trig functions. And so when we're in the first quadrant, this looks like infinity minus infinity indeterminate form. Okay, so how can I rewrite this as a quotient? Well, cosecant is 1 over sine, and cotangent is cosine of x divided by sine of x. So now I've got this limit of 1 minus cosine of x over sine of x. All I did was rewrite those as fractions and combine them. And now what do I see? Well, when x is 0, I get 1 minus 1. That's 0 over 0 indeterminate form. So now I can apply L'Hopital's rule. And again, we know that because it's an indeterminate form, we should get an indeterminate form when we manipulate it. But making sure that you've done the right manipulation is important. So checking that you're still in indeterminate form will help avoid any problems there. Now when I take the derivative of the top and bottom, up top we're just going to get sine of x. Bottom we get cosine of x. Cosine of x for x equal to 0 is 1. Sine is 0. 0 divided by 1 is just 0. All right, that's it for that one. All right, so now we'll talk about one more type of indeterminate form, which is indeterminate powers. Now there's 3 subtypes here. So this is 0 to the 0, infinity to the 0, or 1 to the infinity. And of course, it should be kind of clear how there's a conflict, why these are indeterminate. Right? If my base is approaching 0, you would expect the value to go to 0. But when we take something to the 0 power, we should get 1. So there's a push and pull between f and g here. F is trying to push the function towards 0. G is trying to push the function towards 1. I do notice an odd little typo here. These should be arrows, but for some reason they are not. On the other hand, with the infinity to the 0 type, if f is approaching infinity, that should grow our function. But if g is approaching 0, that should push our function towards 1. So there's a conflict there. And 1 to the infinity type, if your base is 1, you expect the function to, if it's approaching 1 as a base, you expect the function to be equal to 1. But if g of x is approaching infinity, then you'd expect that to grow the value of the function. So again, indeterminate. So in the case of these, what we do is just a clever little trick using inverse functions. We know that e to the ln of, I'll use z here, is always equal to z. So all I do is rewrite my function f to the g power as e to the ln of f to the g power. And that lets me use my power rule for the natural log to move g of x in front of the natural log. And so when I take my limit, I'm missing some more arrows. There we go. When I take my limit, I can move that limit inside the exponential function. We might remember the continuity and convergence theorem that says we can move that limit inside of a continuous function. And so the result of the limit would be just e to the power of this limit, g of x times ln of f of x. That's going to allow us to manipulate this thing a little further, put it in a quotient form after that, and evaluate these things. So let's take a look at that in this next example. The limit as x goes to 0 from the right of x to the x power. So this is 0 to the 0 indeterminate form. So I'll rewrite this limit as the limit as x goes to 0 from the right of e to the natural log of x to the x power, which is e, so I'm moving my limit inside. I'm doing 2 small steps at once, move the limit inside, and use my power rule on the logarithm to write this as x times ln of x. Now I need to rewrite this as a quotient still, so this will be e to the limit as x goes to 0 from the right of the natural log of x divided by 1 over x, or x to the negative first power. So I've written it in this form. Instead of moving the natural log down, then I would have had a composite function in the denominator, would have made the derivative more complicated. I moved the x down because then I have a negative exponent, and that's just power rule. So that's a little easier to deal with. So when I look at this, as x approaches 0 from the right, this is negative infinity over infinity indeterminate form. Doesn't matter if it's plus or minus infinity there. Okay, so we can apply L'Hopital's rule. And we get e to the limit as x approaches 0 from the right of 1 over x divided by negative x to the negative second. So now we're just going to rewrite this thing a little bit here. A little bit of algebra. 1 over x divided by negative 1 over x squared. So instead of dividing, I will multiply by the reciprocal. And when I multiply by x squared over 1, right, I'll get just negative x. And so when x goes to 0, this goes to 0. This is e to the 0, which is 1. All right, that's it for that example. And we're going to just tackle one more example with this indeterminate powers. So when x goes to infinity here, my base inside parentheses here is also approaching infinity, but 1 over x is approaching 0. So this is infinity to the 0 indeterminate form. So this looks a little odd because we're going to have an exponential function inside an exponential function, but that doesn't cause any problems. This will be e to the natural log of e to the x plus x to the 1 over x. I move the 1 over x in front. And now I'll move my limit inside the power. And so now what I see is in my exponent, this limit is infinity over infinity indeterminate form. And so I can apply L'Hopital's rule. And I get e to the limit as x goes to infinity of, in the denominator I just get 1, and in the numerator I get 1 over e to the x plus x times, so this is the chain rule, times the derivative of my inner function, which is e to the x plus 1. And so when I rewrite this a little bit, I get e to the limit as x goes to infinity of e to the x plus 1 over e to the x plus x. And, well, what do I see here? Before I move forward, I see, oh, I have another infinity over infinity indeterminate form. Which means I can apply L'Hopital's rule again. And here I just get e to the x over e to the x plus 1. Now I could apply L'Hopital's rule again, actually, or I could just multiply 1 over e to the x on the top and bottom here. This now looks like one of my basic problems from earlier in the course. And I get 1 over 1 plus 1 over e to the x. So this thing, 1 over e to the x, goes to 0. And then I just get left with 1, so this is e to the first power, which is just e. All right, well, that's it for this video. Thank you for watching.